Now see enthalpy of neutralization. So see dear students, now little bit more focus is required because you have to visualize certain things whenever you are trying to understand this kind of processes and systems, right? See, first I'm defining this enthalpy of neutralization. After that, I will break up each and every step in the definite path. What we have done in already done in our physical processes like isobaric, isophoric process path. So here also I will try to explain you. Different steps involved in a complete and complex reaction what we are getting. Suppose that neutralization reaction, it is very easy. Everybody is saying, okay, acid reacts with base and forms salt and water. This is neutralization reaction, and in this, whatever energy is changing, that is called enthalpy of neutralization. But this, this much explanation or this much of information is not sufficient to understand the concept of neutralization or any such concept. So first I am defining this. After that I will show you the different steps what involve a single, little bit step if involve any, then that also related to something energies involved in that step. So you have to visualize those steps. Mere definition will not work until or unless you have not see each and every part in biological system. In biology, what we can say post-mortem, right? So I will try to post-mortem and try to explain the whole system, right, in terms of this neutralization reaction. And similarly, the other enthalpies are also required to the deep visualization inside the system. So see, enthalpy of neutralization, this is defined because see, this is standard. So standard should be covered with some definition. So a standard enthalpy of neutralization or enthalpy of neutralization, this is defined as the net heat change, the net heat change, when 1 mole, 1 mole monoprotic acid, monoprotic strong acid, completely reacts with, when 1 mole monoprotic strong acid aqueous solution, right? Because the words are very important, and this will these words will help you. 1 mole monoprotic strong acid aqueous solution, right, reacts with, completely reacts with, reacts with 1 mole monoacidic, strong base aqueous solution under standard conditions. Under standard conditions. So all of you are well aware of this standard condition, means 1 bar pressure and at any constant temperature. See here the aqueous solution, This is very important. See here, there is no restriction of volume. Nothing is, any restriction. The restriction is that 1 mole aqueous solution that should completely react. So see, suppose that if we take a beaker, if we take a beaker and some water we take here, and we put HCl in this, and NaOH is this monoprotic and monoacidic base. So suppose that we mix this and this here directly, HCl 1 mole of this and 1 mole of this. So whatsoever energy is changing here, that is called enthalpy of neutralization. Enthalpy of neutralization, standard enthalpy of neutralization. The answer is no, not at all. This method or this process is not included here in the definition. What definition is stating that 1 mole aqueous solution of strong acid. So means what you do, you take 1 mole means such quantity of solution where your HCl is 1 mole. HCl must be there 1 mole, not 1 molar solution. I am not telling 1 molar solution. 1 molar solution may or may not have, right, 1 mole of HCl. Here the requirement is 1 mole. First requirement is 1 mole of HCl should be there. 1 mole of strong acid should be there, not 1 molar. That's why I have not written here 1 molar aqueous solution. Because if you take 1 drop of any 1 molar solution, then that the molarity is 1 molar, but not the 1 mole of quantity of solute is there. Okay, everybody should focus here, otherwise I am sorry, you will not understand. So 1 mole you take any amount of this solution in which 1 mole of HCl is mandatory. So 1 mole of HCl, what will happen when this HCl is put in water? What will happen? You have to visualize this step also, and this is also some energy demanding step or energy change involved here, and this energy is not included in the enthalpy of neutralization, dear students. When, see, this is a process, this is a step. When you take 1 mole pure HCl and you are making aqueous solution, that's why I have written here aqueous solution. So when you are taking 1 mole of HCl in aqueous solution, there is some change. What is the change? HCl, when you are taking pure, this is undissociated. So when you take this in the excess of water, 1 mole of this, so this will dissociate and this will form H plus aqueous and Cl minus aqueous. Large excess of water is there. So H plus and Cl minus, this is a dissociation, and delta H dissociation is involved here, and this is definitely positive. Definitely positive. So remember, dear students, this energy is not included in this enthalpy of neutralization. Remember, right? Clear? That's why it is stated here 1 mole net heat change when 1 mole monoprotic strong acid aqueous solution, right? Similarly, you take 1 mole of NaOH, do the same thing, 1 mole NaOH, right? So delta H dissociation is positive here, and one more step. Remember, this after dissociation. So see, wait, I will express this into different. This step I am splitting in two steps. First, this dissociation of HCl into H plus Cl minus. So here delta H dissociation is involved, and then this H plus and Cl minus, they hydrate in water. So delta H hydration, delta H not hydration, delta H not hydration, this is involved to make this Cl minus aqueous. So this is positive, this is positive, dissociation is positive, but these two are negative. So but this part, this hydration energy and this dissociation energy is not the part of enthalpy of neutralization. So I have broken this complete step into different steps. First, this will dissociate into H plus and Cl minus, and after that this H plus will hydrate with water, that is the association, and definitely this is what? Negative. This hydration is negative, this is negative, this is negative. So this type and this kind of visualization is required to understand the thermodynamics. And delta H dissociation, this is positive. Until or unless you are not involved at this level, you just mere remember and learn and do the things, but in IIT-JEE you will face the problem. Okay. Similarly, this NaOH, so neither this part nor this part nor this part is involved in the enthalpy of neutralization. Similarly, same story with this NaOH. First, NaOH will dissociate into Na plus OH minus, and then they will hydrate with water, and forms Na plus aqueous and OH minus aqueous, right? So this is the direct step, and this is indirect step. Same story, delta H dissociation, and this is delta H hydration. Right. So all these parts are not involved in the enthalpy of neutralization. That's why we have taken this strong acid, because you know in strong acid and strong base, they are fully dissociated, they are fully hydrated before mixing, right? So all these energies are excluded from the enthalpy of neutralization. But once you take any one component is weak or both the components are weak, then the problem is there. Then the energy change in that reaction is not said to be enthalpy of neutralization. If any one component is weak here, either weak acid or weak base, then all these steps are not fully shifted in the right hand side, or means not fully fully dissociated. So that energy is not called enthalpy of neutralization. The enthalpy of neutralization, this is standard, and this is only for this strong acid and strong base. Since in a strong acid and strong base, all these steps are fully completed. Agreed? Clear? So when you mix these two solutions, after mixing these two solutions, whatsoever energy is changing, that is called enthalpy of neutralization. So when you mix these two, now try to develop the ability to look inside the beaker. So when this H plus aqueous plus Cl minus aqueous, they are in the interaction with Na plus aqueous plus OH minus aqueous. So what is happening basically in this beaker, the the process which is taking place in this beaker is the formation of H2O liquid, because in the right hand side Na plus aqueous and Cl minus aqueous both are present in the right hand side as well, because there is no net change in the state of Na plus and Cl minus. There is no bond formation between Na plus and Na plus and Cl minus. They are freely enjoying in this aqueous medium. There is no interaction between Na plus Cl minus, means there is no energy change between this Na plus and Cl minus. And I have this evidence as well regarding my this statement, that why this energy, enthalpy of neutralization. If you go through your table, data, thermodynamic data, then you will find that it is irrespective of any strong acid. Means in place of HCl, if you take HNO3, the same value is coming, If you take in place of NaOH, KOH, then the same value is coming, this enthalpy of neutralization. So it suggests that there is no change in the state of Na plus and Cl minus after mixing. Before mixing and after mixing, there is no change in the state of Na plus and Cl minus. The only change what is taking place, that is combination of H plus aqueous and OH minus aqueous to form water, and whatsoever the energy is changing in this step, that is called standard enthalpy of neutralization. Standard enthalpy of neutralization, and this is minus 55.9 kilojoules per mole, and it is constant for all strong acid and strong base. Means if you take HCl plus NaOH, this is, if you take HNO3 plus NaOH, the same energy will change. If you take HCl and KOH, if you take half mole of H2SO4, because this is diprotic acid, so 2 moles of H plus will come, plus NaOH, then you will get the same. So see, this is basically the energy changing in this step only, H plus aqueous plus OH minus aqueous. This is called enthalpy of neutralization, and this is equal to minus 13.7 kilocalorie per mole, or minus 55.9 kilojoules per mole, and this is constant for strong acid and strong base. Hopefully all of you are clear. Now I am giving you a very general equation, and I'm also expecting from you people that you should follow that general expression for the calculation of enthalpy of neutralization and other calculations in the similar reactions or similar question. Suppose that I have Ha, one acid. I am not mentioning that this is a strong acid or a strong base. This is an acid, and Hb is a base. This is also, I'm not mentioning here that this is weak acid or strong acid, weak base or strong base, and this is weak acid or strong acid. This will first dissociate when you dissolve this in aqueous medium, H plus aqueous plus A minus aqueous, and this also dissociate plus Oh, sorry. Here this is not HB, this is BOH. BOH. B plus aqueous plus OH minus aqueous. And this will give you the H2O liquid, and I am ignoring this A minus aqueous and B plus aqueous, right? So, see, delta H dissociation here, delta H dissociation here. I'm not considering here, I mean, hydration, because that will, I'm not here, because we are mixing solutions, so hydration energy is going out. So hydration energy is not considered here. So this is for acid and this is for base, right? So, what is the enthalpy change of this reaction? The enthalpy change of this reaction, I am not telling this is a neutralization reaction. This is an acid-base reaction. So, enthalpy change of this reaction is equal to this dissociation, delta H dissociation of acid plus delta H dissociation of base plus delta H not neutralization. So this is a master equation. Now we can change different terms here, and we define this. Now see, if the acid is strong, then delta H dissociation is equal to 0 in this equation, because this is already dissociated. This will not considered here. And base is also strong. Then delta H dissociation for base, this is also 0, acid and base, right? This is also 0. Clear? So now this equation is reduced like this. Delta H not reaction is equal to delta neutralization H naught, right? Equation 2. Okay. When acid is weak, suppose that acid is weak, so delta H dissociation, some dissociation is, some molecules are dissociated, but most of the molecules are not dissociated. So this is not equal to 0. And base is strong. Then delta H dissociation is equal to 0. Then the delta H naught of the reaction, above reaction, is equal to delta H dissociation of acid plus delta H neutralization, right? So this is equation 3. So delta H naught neutralization means every time you can say that energy change in the combination of H plus aqueous and OH minus aqueous, right? Similarly, you can make other cases as well, right? When base is weak and acid is strong, then if base is weak, then this is not 0 and this is 0, then this is equal to this. So sometimes examiner will give you similar questions, so you can you are able to solve this. And remember one thing, that for any other pair of acid base, suppose that is strong acid plus weak base, The enthalpy of neutralization or enthalpy of reaction, more appropriately we can say, this is less than the enthalpy of neutralization, means minus 13.7 kilocalorie per mole. Don't consider sign here, you consider only magnitude. So basically this value is lower than this, means minus 12, minus 11, minus 10, like that. Strong acid, weak base, or weak acid, strong base, right? Or weak acid, weak base. For any, pair, this is always true. Okay. So consider only magnitude, don't consider sign here when you are comparing the delta H, right? One exception is there. One exception is there. When your acid is HF, when acid is HF, this is a weak acid. And if you take the energy of this reaction, enthalpy change of this reaction, so you will find this NaF plus H2O, the reaction enthalpy of this reaction is minus 16 point minus 16 kilocalorie per mole, and this is greater than minus 13.7 kilocalorie per mole. Why? Why this is greater? So see, now you have to visualize inside the beaker. When you are making this HF solution, so what will happen? This HF is partially dissociated and most of the molecules are undissociated, H plus aqueous and F minus aqueous. This is the solution of acid when you have made. This is the equilibrium. Most of the molecules are undissociated since it is a weak acid. And this is a strong base, so this NaOH is fully dissociated, 100% dissociated in Na plus and OH minus NaOH. Right? Clear to everybody? Okay, good. Now when you mix these two solutions having 1 mole each, 1 mole each, 1 mole of this, so some part of this is undissociated, maximum part is undissociated, some part is only dissociated. So when you mix these two, what will happen? Some energy is going to dissociate this HF and some energy is released in the hydration. So remember in the first, in the beginning of this, I have told you, so there is no change in the state of this Na plus is always there, OH minus is there. Now this undissociated HF acid will start dissociating, and once this start dissociating after mixing, not before mixing. So after mixing, if it is start dissociating, so after mixing there are two steps. First this will dissociate, and after that water is there, so hydration is there. So what will happen? This H plus aqueous is formed, F minus aqueous is formed, so a large amount of energy will release. Large. So in the case of other cases, like in weak acid or weak base, obviously this is releasing. So but in those cases, this dissociation, delta H dissociation, is more than the amount of energy released here. But in this case, due to very small of this fluoride ion, very small ion, this F minus ion, so very small size, due to this large hydration energy will release here. So that will overcome this dissociation, and in fact it is added in the enthalpy of neutralization or enthalpy of this reaction. Getting my point? Again I am repeating. Listen carefully. When you take HF, it is partially dissociated. Okay, this is fully dissociated. When you are mixing these two, and remember my organic chemistry lecture in which I have categorically say that in a same beaker, if you are taking weak acid and strong base, don't expect that this weak acid is forever present there undissociated. Now this will forcefully will dissociated by this NaOH, and no one acid is behave like a weak acid in the combination with the strong base. A strong base will force this HF to get dissociate to complete the neutralization. So this HF will dissociate. When HF will dissociate, this dissociation energy is endothermic. H plus will hydrate, F minus will hydrate. This is exothermic process. So energy will release. That will overcome this amount, and some amount is added here in this reaction. Because after mixing there is a dissociation and hydration. In case of strong acid, strong base, before mixing, hydration and dissociation, all steps are completed. But what about in these cases, weak acid, weak base, weak acid, weak base, strong acid? In all these cases, the size of anion is not so small, so that the hydration, because H plus is common everywhere, H plus is common, right? So in every case, H plus is common. So I will not explain this. I cannot explain on the basis of H plus. The only difference I am getting here with respect to F minus and other anions. So other anions are relatively larger in size. Therefore, in those cases, energy release is less compared to this. So here, energy release more in case of F minus. This is the reason why the enthalpy of reaction, I cannot say enthalpy of neutralization, this. So enthalpy of this reaction is more than the enthalpy of neutralization. So dear students, all of you should remember this. This is very important case, right? So this is the enthalpy of neutralization and different aspects, but many questions are framed in a different aspect of this. So again, I am writing one more time that equation, that is fundamental equation, H plus aqueous plus OH minus aqueous. This will give you H2O liquid, and delta H neutralization is equal to minus 55.9 kilojoules per mole. So this enthalpy of neutralization, which is for strong acid and strong base, this is also called, or you can say, this is the enthalpy of formation of 1 mole of water, 1 mole of water from H plus aqueous and OH minus aqueous, right? We can say. Now see how this is useful for us. Suppose that it is given that we have 1 mole 500 ml H2SO4 and 1 mole 500 ml NaOH. Suppose that the question is asked that now see these two are mixed. Then how much heat energy released from system? So this is very simple calculation. You just focus to calculate the number of moles of water formed. That's it. If you are able to find out how many moles of water will form here in this combination, very easily you can calculate the amount of heat energy released, right? So how to proceed this question? All of you are knowing that one very effective calculation, millicurrents calculation we have. So if we apply millicurrents calculation, then it is very easy. See, now you have to calculate millicurrents of H2SO4 present here, millicurrents of NaOH, because equal millicurrents of this will neutralize. So millicurrents of H2SO4, and they will not change when there is a dilution of any solution or mixing, after mixing. So millicurrents of H2SO4, originally what you have, that is equal to molarity, sorry, moles are 1, n factor for H2SO4 is 2 into 1000, right? So this is the millicurrents of H2SO4. This is 500 ml or 1000 ml. Here it is not the part of our this calculation, right? So don't see that, because that will not affect your heat, right? Temperature may be affected, but not heat. So this is equal to 2000 millicurrents of H2SO4. We have originally millicurrents of NaOH is equal to 1 into n factor is 1 into 1000. So this is 1000 millicurrents. So is there a complete reaction between these two? The answer is no. Only 1000 millicurrents of H2SO4 will combine, and 1000 of this, and 1000 millicurrents of H2SO4 will be left behind. So the reaction between these two is H2SO4 plus NaOH will give you Na2SO4 plus H2O. Basically, our focus is to find out the moles of H2O, right? So millicurrents of H2SO4 is equal to millicurrents of NaOH is equal to millicurrents of H2O, right? But this time the limiting reactant is NaOH. This is limiting reactant. So millicurrents of H2O is equal to millicurrents of NaOH, not the millicurrents of H2SO4 taken. So as per the quantitative rule, we can write here millicurrents of H2O is equal to millicurrents of NaOH, because this is limiting reactant. And all of you are knowing that in terms of millicurrents, the reactant of which millicurrent is less, that is limiting. Straightforward. No need to balance and all, do all those things. So millicurrents of NaOH is equal to 1000. Now you apply the formula of moles here. So moles of water into n factor in this reaction. See, in other reactions, n factor for water is 2, but here the n factor for water is 1, remember. So n factor for water is 1 here. So this is into 1000 is equal to 1000. So this is cancelled. So moles of water is equal to 1. So if there is 1 mole of water, formation of water is taking place here. So the heat energy, enthalpy of neutralization, it is defined with respect to this. So this is minus 55.9 kilojoules. So this energy will release from the system. So how much heat energy is released from the system? So the answer is, don't write negative. you have to write 55.9 kilojoules per mole. Never write negative here, because in the question they have already written how much heat energy released. Release means negative sign is already there. No need to write negative here. So amount of energy released from the system is 55.9. So this is the best way to solve such type of questions, right? Every time your focus is what? To find the number of moles of water formed, and accordingly you can manipulate the amount of energy released from the system. Clear? So this type of questions you may get, right? So means effectively 1 mole of water is formed when you mix this 1 mole of 500 ml H2SO4 and 1 mole of 500 ml NaOH. Clear to everybody? Okay, good. Now see, this is a question. So heat of neutralization of HCN with NaOH is minus 12.13. So this is less than 55.9 kilojoules per mole. So definitely this is not a strong acid, strong base enthalpy of neutralization or heat of neutralization. So and everybody is knowing this is a strong base. So this is just weak acid basically. HCN is very weak acid. Find delta H ionization. So weak acid is strong base, right? So if you want, you can make the equation that HCN plus NaOH and this NaCN plus H2O, delta H not neutralization of this is given minus 12.13 kilojoules per mole, right? Now we have to find out delta H ionization, right? So delta H ionization means delta H for dissociation of this H plus aqueous and Cn minus aqueous. Right? So if you want, you can write equations and then you can easily, find to this. Or if you want, you can directly use, I have given you that delta H of this neutralization reaction or reaction is equal to delta H ionization plus delta H neutralization. And you know this delta H neutralization standard this is fixed value 55.9 kilojoules per mole, right? So the reaction is given minus 12.13 minus 12.13 is equal to, this is asked, plus minus 55.9. So delta H ionization this is equal to what? 55.9 minus 12.13. This is equal to 43.77 kilojoules per mole. And this is the answer. Right? So in this way you can calculate the delta H ionization, whether you are using this equation what I have given you, this general form master equation, or if you want then you can write, see, H plus aqueous plus OH minus aqueous. This will give you H2O liquid. Delta H neutralization is equal to minus 55.9 kilojoules per mole. This is a standard equation, and this will not be given to you in any question. This you have to use from your side. So this is a standard equation, right? And if you want to calculate this enthalpy of this, and you have one more reaction is this. So you have this reaction and this reaction. So manipulate this reaction in such a way that you will get this reaction, right? So this you can write here HCN whatsoever you have taken, that is H plus plus Cn minus plus fully dissociated Na plus plus OH minus. This will give you the NaCN plus H2O liquid. So basically you want to delta H of this, and delta H of this is known, and delta H of this reaction is known. So how to get the delta H of this? So you can write this, the delta H dissociation, delta H dissociation plus delta H of this reaction, this is equal to see, delta H dissociation plus delta H neutralization of this H plus and OH minus. This will form this H2O liquid, right? This is equal to delta H of this complete reaction, delta H of this reaction, right? So basically this you have to find out this dissociation. So this is one step, and this combination is step 2, and this whole reaction is the combination of 1 and 2. So basically this is 1 and this is what, 2, right? And this is equal to this complete step. So this plus this is equal to this complete reaction. So in this way you can find out the delta H, means amount of energy required to dissociate this HCl into H plus and Cl minus, right? So in this way you can solve, and you can do the problems based on this neutralization step.